Hi everyone, I'm Zahra I'm a PhD student in Environmental Sciences Department uh, at University of California, Riverside. I'm working with Dr. Verdis, and today it's my pleasure to share some of my results with you. So first of all, it is more than half of the world's population was inhabited in cities in 2018, and it is projected that global urban population will increase by 70% in near future. As with the rise of population, urban green spaces are getting increasingly valued because they provide us different ecosystem benefits, such as human health, well-being, and also environmental qualities. On the other hand, a considerable fraction of urban water goes directly for urban irrigation. About 40 to 70% of total water use in urban areas goes directly for residential area to irrigate their lawns or landscapes. So therefore, it is important to develop landscape conversion Therefore, it is important to develop water conservation strategies, especially for western side of United States, like California, and as a response, Los Angeles. With other cities like Phoenix and Las Vegas have initiated landscape conversion programs that they encourage residents to replace their lawns with drought tolerance ground covers. So the question is, so the assumption is that these ground covers require less water, but there is limited research that they actually quantify their actual water needs. Urban heat island is a major phenomenon is a major problem in urban settings, which means the higher temperature in urban settings compared to rural areas, because the expansion of impervious surfaces such as asphalt and also replacing plants with these impervious surfaces. So beside the benefits of urban greenery I mentioned in previous slide, so these landscape plants also provide cooling benefits through different mechanisms, such as shading, reflecting the sun back, and also evapotranspiration, which today I mainly focus on evapotranspiration part. And there are some questions which I'm particularly interested to answer. First of all, before jumping to questions, I want to give you a brief description what is evapotranspiration. So when we apply water to when plants receive water from precipitation and also irrigation, they uptake water, and also they lost water through transpiration and also through evaporation from soil surface and also plant materials. So this is an energy consuming mechanism, and all through this mechanism they provide cooling benefits for us. So as we apply irrigation, deficit irrigation, so the transpiration rates decrease, and also the cooling benefits may or may not be impacted. So the first question is that if we draw some water conservation strategies, so how it will impact on cooling potential of these ground covers. And the second question is the plant choice. So for when deselecting drought-tolerant plants, so should we also consider the cooling potential? And also, finally, I'm very interested in what is happening on below the ground. So how root system contribute to cooling benefits of these species, cooling effects of these species. I did a lot of work on this part, and also I measured root systems and also plant measurement, and a lot of modeling work, which I'm not presenting today, but I briefly touch onto the main conclusion we got from numerical model. So the actual water, so the question is, what is the actual water requirement of these ground covers based on minimum, maintaining minimum water, maintaining minimum visual quality, and also how deficit irrigation will impact on these ground covers. So the objective of this study is to evaluate the response of these ground covers when they exposed to deficit irrigation, and draw irrigation recommendations based on minimum acceptable visual quality, and also providing cooling effects. So we planted 4 ground cover species in UC Riverside Agricultural Experiment in Ag-Up in Riverside. And so we selected 1 woody species, prostrate acacia, which I'm presenting the informal name, not the scientific name. So it's a woody species, and it's from Australia. 2 herbaceous species, African daisy and Balbieto from South Africa, and Crappia from Japan, which is a grass species. On the right hand side, you see one of the drone images I took in March 2023 from my plots. So we apply 4 irrigation levels from 20% to 80% of potential evapotranspiration, and irrigation application was automatically done with a weathermetric ET-based smart irrigation controller, and also we have the wireless weather sensor to estimate daily potential evapotranspiration. We also apply irrigation treatments from April to October 2022 and 2023. So to quantify the response of these ground cover species, we measure 3 indices. The first one is visual quality. So visual quality of this species is rated from 1 to 9. None means dead plant, 6 is the minimum acceptable appearance, and 9 is the healthy plant. And also for the cooling effects of these species, we measure canopy temperature with a handheld sensor, and we calculate this index delta T. So which is canopy minus air temperature. If canopy temperature is less than air temperature, which means that that plant is not contributing to cool the environment. But if this species is greater than, if this index is less than 0, which means that canopy temperature is less than air temperature, and this species is contributing to cool the environment. But if delta T is greater than 0, which means that canopy temperature is greater than air temperature, and this species is not contributing to cool the environment. And last one is normalized difference vegetation index. So this index is a widely used index in scientific community to quantify the health of vegetation, and the higher value, which means that that plant is in a good condition. And we measure it through a handheld sensor by measuring two near infrared and red bands, and this instrument will automatically calculate NDVI. So in this slide, I'm showing you how these species respond to deficit irrigation. First of all, in the first row of picture, so you see the prostrate acacia, the normalized difference vegetation index, which if this index doesn't change that much, which means that this plant is doing good when exposing deficit irrigation. So and on the other hand, on the right side, so you see canopy picture and canopy temperature. So prostrate acacia performed good when we applied deficit irrigation, when we cut water from full irrigation to 25% potential evapotranspiration, and canopy temperature only increased about 4 degrees. But for Coroppia, so the last row, so Coroppia was the most sensitive species to deficit irrigation, and as soon as we applied deficit irrigation, the NDVI dropped dramatically across different deficit irrigation treatments, and also canopy temperature was up to 20 degrees higher in lowest irrigation treatments compared to full irrigation treatments. So in this picture, I'm showing you delta T, which I mentioned is canopy temperature minus air temperature, and blue shade area shows that measurements that canopy temperature is less than air temperature, and which means that these plants contribute to cool the environment. So for prostrate acacia, so you see that most of the measurements are below in blue area, which means that this plant did great when we applied it did great to cool the environment when we apply deficit irrigation. But for Coroppia, you see that most of the readings are above are not in blue shade area, which means that the canopy temperature of these species are higher than air temperature, and they did not contribute to cool the environment even we apply full irrigation treatment. So as conclusion, so plant choice matters, as you see that plants behave differently to deficit irrigation. Prostrate acacia was the least sensitive species to deficit irrigation, compared to Coroppia was the most sensitive species to deficit irrigation, and even applying 100% evapotranspiration, this plant cannot maintain its canopy cooler than air temperature. And also I quantify the contribution of root system to cool the environment, to cooling effects. In the left-hand side pictures, you see root and plant measurements we've done in lab in December 2022, and we use this measurement as an input for a numerical model, which is HYDROS. And the result of HYDROS shows that plants adapt different mechanisms to, first of all, withstand with drought. The first one is that they develop deep roots, and through deep roots they uptake water. And the second one is compensated root water uptake, which means that if we have two areas in the soil, wet and dry soil, plants uptake more water from wet soil when this plant is under stress, and in this way, this plant can fulfill water requirement. Its water requirement. So the future work is that this year we simulate extreme water conservation. We cut off water from May until now, and we also collect the same measurement, and we want to see how these ground covers respond to 1 year without water. And the second one is I'm going deep into other cooling mechanisms. In the second slide, I mentioned about reflecting sun back and the ability of these plants to reflect the sun back to the environment. And right now, we are measuring albedo in the field. So thank you so much for your attention.